Sorry. So, can you hear me at the moment? Okay. So thank you, Zulaika, for the introduction. So I would like to welcome all of you, and good morning, everyone, and thank you for joining us for today's webinar series again. So, for today webinar will be about basic nonlinear structure analysis. Okay, as you know, this topic is so extensive, so we unable to cover everything. But for today, we will cover several topics, which include what is the nonlinear behavior, type of nonlinearity, nonlinear solution using a linear solver, and then we also will discuss about the nonlinear finite element analysis issue. So we hope this webinar help you understand about the fundamental nature of nonlinear finite element analysis. So before we begin more deep about the nonlinear behavior, I think better we talk first about linear behavior. So the linear behavior was first described by the Robert Hooke. Okay, so this F equal to KU or F equal to KX is a Hooke's law. So the force in the spring is directly proportional to displacement. That is based on the Hooke's law. So the constant of the linear relationship are known as stiffness. And then linear behavior structure are very well suited for the doing FEA analysis. Okay, but in the real world, many structure don't have in a linear manner. So in a non-linear problem, the stiffness change depending on the amount of fluid or deformation that take place within the structure. Okay, so for the nonlinear behavior, the stiffness is called a tangent stiffness. Okay, that which represent the tangent to the force deflection curve at the particular point on the load path. Okay, so next we will cover about the nonlinear analysis. Okay, so for the nonlinear analysis, begin exhibit due to three factors, which is the strain beyond the elastic limit, and then large deflection, and then a changing status. Okay, so this is a type of nonlinear. So basically for nonlinear analysis, we have three type of nonlinear, which is the geometry, boundary contact, and material. Okay, but for today webinar, I think I will cover about two type only of nonlinear behavior, which is geometry and contact. Okay, so you can refer to the image one, which is about the fishing pole. So when you apply load at the tip of the fishing pole, you can see deflection. So this is related to geometry nonlinear behavior. And then for contact nonlinear usually happen when you add the assembler component. So it happen when you changing a context status. Okay, so to activate the nonlinear solution, you can turn on the several option and material property as shown here. Okay, so I think so for the first demonstration, I will is related to a nonlinear geometry problem. So I use a translational join model for the simulation. Basically, a translational join is used to connect two machine component so that the relative motion of two component is restricted to the translational in a specific direction. For this model, POM, which stand for the polyoxymethylene, was used as the main material. Okay, let's start with the simulation. So, um, actually, I already export the geometry here. Okay, and then I link to the static structural problem. So, we can go click to the engineering data to check the material properties. So for POM, so this is the material properties for the polyoxymethylene. So it has the 2 exponent 9 Pascal, and the polarization is 0.35. Okay, so we can close the engineering data. Okay, so after that, we can go to the model to begin the simulation. So we edit here. We click edit. Okay. Okay. So this is the component. So first, what we need to do is to check the unit. So for this simulation, I use a metric. So mm, kg, Newton, and so on. So and then we can go to the geometry to check the model. So this is our model. So we can go to display and then click cross section lah to see the model. So this is the model lah for the transitional joint. Okay. Then we need to make sure that we use the correct material. So for this case, we used the material is a polyoxymethylene. Okay, and then so after that we can generate the mesh. So this is the mesh after generate. Okay, so first we need to perform the elastic behavior. Okay, actually this model based on the elastic first. Later we want to see the difference between the elastic and not sorry, this is a elastic and a linear problem lah. Okay, and then later we want to compare the linear and the result from the linear and non-linear. Okay, so first so so we're done with the meshing. Then next we want to apply the boundary condition. So for the boundary condition, we will Okay, we will use remote displacement. Okay, and then because later because I want to fit at this point, then click apply and then set all the component 0. So that's mean at this point is fixed. Okay, and then later I use a displayment at this point. Okay, so for this point, I will apply about 40 mm in the x direction, and then the other component I set 0. Okay, so this one for the solution, I will select the we want we want output the output is a total deformation and force reaction. For the force reaction, we will select the displacement. Okay, now for the linear behavior, we set the large deflection is off. Okay. Later for the non-linear behavior, we will turn large deflection on. So now we can solve this problem to get the linear result, linear behavior result. Okay, so this is the result for um linear behavior. So but we interest in the force reaction. So as you can see here, the value for force reaction is about 74.6. Okay. Okay. Next, actually we run the simulation. But for the nonlinear behavior. Okay. So for the non-linear behavior, actually we set the similar setting. So so for I fix at this point. And then I put displacement at this point. And then I set 40 at the exponent and then set at the component 0. Okay, but for okay, I left default first for the step control. Later I will explain about the step control. But for this time, I will turn on the large deflection. Okay, so the output is the same, total deformation and force reaction. So okay, now it's ready to be solved. Okay. Okay, sorry. Actually, you need to set the step control. Before that, I will explain about the step control. So, so this is the to perform the nonlinear behavior analysis. Actually, you need to apply the step control. Okay, so step is the load history of the analysis consists of one or more step, and then the other one is the substep. Substep is part of a step in a nonlinear problem. Total load applied in the step is broken into the small substep so that the linear solution path may be followed. And then the last one is an iteration. And iteration is an attempt to finding equilibrium solution for the substep. Okay, so for this case, I will use this setting. So for the initial, I will set 0.1, and then for the initial this minimum is 0.01, and then for the maximum is 1. So 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 this is explanation lah. What will happen if we use the time step. If the conversion behavior is very good, it may increase the time step, typically 50% for the next sub step. And then if the conversion behavior is very good, it may increase the time step, typically 50% for the next sub step. Okay, so we go back to the analysis setting. Um, So for this one, I will turn on, and then I will set this initial substate is 0.1. So a change to time. So this is 0.1, and then this is 0.01, and then the maximum time tag is 1. Okay. So now we can run the we can solve the problem already. Sorry, so sorry for technical issue. Okay, so for this one, okay, so this the total reaction. So as the linear behavior, we only get about 74. Okay, and then but for the non-linear is 145. So okay, and then okay, this is the calculation lah. For the how they get the time, calculated time. So so for the initial substat, you start with 0.1, and then for the next substat is continue with the 0.2. So this is the, and then if the conversion is okay, and then it will increase about 50%, as I mentioned earlier. So so it will follow this trend lah. Okay, so until the iteration complete. Okay, this to make sure the, okay, to obtain the more accurate data, actually we can modify the time step. Actually, we go to the analysis setting, and then we can actually we set the displacement previously is 40. So so we may set step and time to 40 seconds, so that each second correspond to millimeter of displacement. Okay, to plot more accurate force versus displacement relation, we need more time step, which preferably distribute evenly. So we can go to analysis setting, and then change this one. We can turn off, and then now we set the time step is 2. So that's mean later we will get the 20 set result. Now we can click solve to obtain the result. So so this is the result lah for force reaction. As you can see, there are 20 set of data. So this actually the time is represent the displacement. So this is analogous to 2 mm until 4 mm. So this is the result lah. So actually uh, we get a better uh, result for the display. Actually this is the result lah. Okay, and then we can repeat the same procedure for the linear problem, and then we can compare lah which one um, we can compare between the linear and non-linear behavior. So as you can see, this is the difference lah between linear and non-linear. So that's mean so so that this justify the need of a non-linear simulation. Okay, next we will continue with the second demonstration, which is related to non-linear contact. Okay, so for the linear contact, this is our model. We is a snap fit buckle. So snapfit bucket is the common attach method to connect two flexible method. This flexible pipe. So for this simulation, we will use ABC plus PC plastic. So he has this following mechanical properties. Okay, so let's begin with the second demonstration. So we go to this workbench, and then as you know, the geometry is already attached to the geometry, and then we will link the geometry to the static structure. Okay, we can click the generate data to check the data. So this is the mechanical properties for the um, ABC plus PC plastic. So actually for this material properties, we add tensile yield strength and tensile ultimate strength. So this is the value lah for the tensile yield strength, which is about 35.1 MPa, and then for the tensile ultimate strength is 45.2. So now we can close the engineer data, and then now we can go to model and click edit. Okay. Okay, so this is our model here. So as usual, we need to check the unit first. So for this demonstration, I use IMM, and then we go to geometry. So we have two component. So this is the first component, and then this is the second. So for the first one, we set we will make sure we use the correct material. So the material is a ABC PC plastic, and then the second one also same. But for the first component, we will set this part as a flexible, and the other one is as a rigid. Okay. Okay, and then next is about contact. So okay, now you see the contact here. The blue one is represent the target, and then the red one is the contact. So um, this is the we will select all the surface on this rigid body as a target, and then the surface on the contact flexible body as the contact. Okay, so total contact is 12 face, and the total target is 14 face. Okay, and then after that we can set this option with the trim contact we set as off, and the other setting we left as a default. Okay. So next we can do the meshing lah. So I already perform the meshing. So this the mesh. So you can apply multi-zone for this component, and then okay, and then for this surface, actually we reduce the number. We increase more element here, so that we can get more accurate data at this point at this surface. And then for the analysis setting, so this is the actually we set two substat here. Okay, for the first one, this is the first one. The current step one is we set the we use this this number as our substep. Okay, and then for the second step, we use this setting. Okay, so for both step, we on the large deflection, and then another one, we need to set the stabilization as a constant. Okay, for both step 1 and step 2, set as the constant. Okay, just want to mention here. So actually, we have five type of contact. So we have a bonded, rough, non-separation, frictionless, and frictional. To activate the non-linear behavior, you need to either select rough, frictionless, or frictional. So rough, frictionless, and frictional is the non-linear contact. Okay. So the contact type bonded and non-separation are called linear contact because they assume small deformation and involve non-linearity. The other contact type will introduce contact non-linearities. Okay, and then this is a non-linear control. Okay, actually for this option, we just left default lah, because the default convergent criterion work very well for most engineering application, but for this case we only change we only change the stabilization into constant. Okay, so constant to maintain the damping factor as a unchanged constant during each substep of a load. So another option for the stabilization is the reduce option. So the reduce option, actually the purpose is to reduce the damping factor linearly to 0 at the end of the load. Okay, so we go back to this simulation. So now we want to we will apply the remote displacement. So for remote displacement, I will set at this surface. Okay, and then I will and then I will set every component 0. Okay, and then I will use a displacement. Okay, then I apply at this surface lah. Okay, and then to check the distance, we select this point and select this point. So you can see here the distance between this the surface is 24.733. Okay, and then so that's mean we need to set only at the z component about 24.7, and then for the other component we set as a 0. Okay, so for the output, we want to determine the total deformation, stabilization energy, and equivalent stress. Okay, now it's ready to solve. We solve, and then just click solve to obtain the result. Okay, so we can go to the solution information. and then to check the false conversion. Okay, so we need to wait until we get the result. Okay, it will take about several minutes to solve the problem. So the purple color is false conversion, and then so false conversion represented by this turquoise color, and then the green. So we get the first subset is already converged. So now deflection occur. So that means um, the result is not really okay. So so that means the value will be reduced. The subset will be reduced. So and then we continue with a new value. Okay. Okay. You also can go to the solver output to check the result.
What na 8.85?
Okay, so you can go to this section lah to check whether you get the value converge or not. So okay, so the result we update here. So you can also use the solver output to determine the problem lah in your analysis. Okay, so usually if got an error, the error we will describe here. So you can check and try to overcome the error in the next in the setting. So now we go back to the false conversion. So you can see here more substate already converged. So it take more iteration to complete. Okay, at the moment, we already complete about 41%. So okay, so now you can see more subset is converged.
Gila. Baik dah kan.
You can also, yeah, you can also check the displacement convergence. But normally we just use the force convergence to check. So I think the simulation is almost complete. So okay, so now the simulation is complete already. So now we can check the result lah. Okay, so this result for deformation. So actually you can play and then see um, the animation here. So this is a net fit. So you also can check the stabilization energy and then the equivalent stress. So that's all for the result for the net fit simulation. So okay, actually, as I mentioned previously, actually you can go to the solution information to get the convergence value and criteria list in the tag form, or you can refer to the force conversion to check the conversion issue. So for to tackle the conversion problem is you need experience and skill um, to overcome the problem. So I think so this is a force conversion just as I mentioned earlier. So I think that's all for today. I open the session for the question. For if you have any question, you can ask me.
Okay.
Or I pass to Zulaika.
All right. Thank you, Dr. Muhammad Azim, for this informative webinar on basic nonlinear analysis. I hope you have been enjoying this presentation so far. I also already launched a poll. Please select the appropriate response and click submit. Now it's time to address your question. Feel free to type your question in the chat features, which you will find at the right at your screen. We will do our best to answer as many questions as possible during this session. So does anyone have question regarding this topic? So the first question is how to calculate time step. So Dr. Azim,
Okay,
may you answer this question?
Okay. Actually, you can set as default at the beginning. So actually, or you can use this setting lah. You can select any number, but for the minimum is normally is 1/10 from the initial step, and then for the maximum is time from the initial time step. So you can set your setting as based on this description. Okay, there are no fixed value for to set the time step. That's all of my answer. I hope answer your question.
Thank you, Mr. Nguyen, for the answer. So
Question.
while we are waiting for the next question, I would like to remind our participant that sometimes it takes a moment for question to be formulated. So don't hesitate to ask about anything related to our discussion today. Indeed, Dr. Azim, it seems that we might not have any question at the moment. Okay. Dr. Azim, is there anything else you wanted to cover?
Nothing. Okay, I think that's all for me today. Thank you.
All right. Thank you, everyone. We appreciate you being here. We also encourage you to connect with us on social media to get the latest information. Don't forget that we will post a recording of this webinar at our YouTube channel. If you have additional question, you may contact us by email or telephone. We are happy to provide additional support. Thank you all for attending. Have a wonderful day.
Thank you.